So the next presentation is event-based control applied to wireless throttling valves, and it will be presented by Terry Blevins from Emerson Process.
Good morning. The presentation addresses wireless throttling valve control. If you look at the process industry overall in general, it's fairly slow to adopt new technologies. It's a very conservative industry. But in the case of wireless control, it's been rather amazing over the last 6 years, the adoption rate of wireless measurements. Initially, wireless measurements were used primarily in terms of just measuring, but there are more and more examples of using wireless in closed-loop control, the wireless measurement. Right now, manufacturers are working on wireless throttling valves. So this allows then a totally wireless control loop, both the measurement and the actuator. And it introduces some new problems that are challenges. So those are the things that I'd like to try to address today. We'll go through a little bit of an introduction and then talk about wireless valves, give some examples of where we've actually worked with those. In terms of sort of some background, if you look at wireless today, there are commercial devices available from multiple manufacturers where you can measure either in a continuous manner or a discrete manner, like here a vibrating fork to indicate a point measurement, either you're above or you're below a point, or a continuous measurement. You have level measurements as well, on-off valves. And in the case of these discrete types of controls where you have an on-off type valve, the actual control is quite simple. It's pretty much nothing more than what you'd have on your thermostat at home. It's just on-off type control with a little bit of deadband in it. But there are a number of published applications where people have used discrete valves with wireless measurements for temperature as well as level control in these slower applications. So the world of discrete control is being addressed. In terms of continuous control, there are a number, just a wide variety of continuous measurements today to now instrument your process control system. And initially those were put in primarily just to monitor what's going on, but I think people have found that the technology is very reliable. And in many cases, rather than just looking at something, they really want to tie it to closed-loop control, actually do closed-loop control. One approach in terms of addressing closed-loop control is to modify your PID algorithm to be event-triggered in terms of the update of the reset contribution and the rate contribution. And that's called PIDPlus, and there are a number of papers and things that we've written about that. But it's a very effective technique in terms of handling the wireless measurement, where the actual tuning of the control is just based strictly on your process dynamics. It's totally independent of the sample rate, doesn't matter. So very, very effective, very robust technique. Now, when we look at that, this is sort of an example of using a wireless measurement using the PID. So we're comparing then a wired measurement with wired valve to a wireless measurement using PIDPlus. And in this case, we're using something called windowed communication, which is a periodic update of your measurement. And as you can see here, it's quite effective in terms of handling both measured, like a change in set point, or an unmeasured disturbance in this case. The control is just a little bit worse. It looks like, if you look at integral of absolute error, it's sort of a performance measure. But in a way, it's sort of an unfair comparison because you're integrating this error here for the wireless, where in actual life, if you can actually sense what's going on in the process, it's very, very close to what the wired measurement was. So very comparable type control with wireless. But the important thing is, by using wireless then and this technique, in this case, the wired control used 692 updates. in that same time frame, the wireless used 25. So just a terrific reduction in number of the measurements that are required to have comparable type control.
The question, what was the performance measure? How do you measure performance?
Just integral of absolute error, the difference between set point and measurement. And as you can see here, in terms of the measurement, these little ups and downs there, in real life, if you can actually sense it, it's not that bad. But now let's get into wireless throttling valve. There are certain applications where there's a real demand for this, and one of them, we hear about fracking and the oil production and that. The actual cost of installing field measurements in these oil fields is quite high. And so if you can eliminate the wires, you can just dramatically save the installation on the installation cost. So there's quite a market demand for wireless throttling valves. Conceptually, if you think about a wireless throttling valve, and you're using it with a wireless measurement, then you'd be taking something like the PIDPlus, and then maybe using the external reset, that is the measured position, coming into this network, the positive feedback network that's used to create the reset action. And conceptually then, should be quite straightforward to incorporate in either a motorized actuator or one that's air operated in terms of a throttling valve. But in practice, there are a number of challenges. The actual communication to the actuator right now is not scheduled. Whereas on your measurement side, all the measurements that are coming in are scheduled. So that means that on your measurement side, very little delay between the actual sensing and using it in control. So you're introducing very little delay or dead time into your control. Whereas here, you can have quite a lengthy delay. And also, in terms of the actual sensing of where the actuator is, the feedback of that in response to a right command can also be quite lengthy in terms of time because it's an unscheduled communication. Now, there are some things that are going on in terms of downstream publishing that are going to improve this, but today there is quite a bit of delay, and even with downstream publishing, you'll still have some delay there. So that's really the challenge. The other thing is if we're using an actuator here, most of the power requirement of the actuator is going to be due to the times when you're actually moving valves. That is, you're actually changing position. If you're not changing position, no real demand in terms of power, but as you change position, that's really where it starts to drain power. So minimizing that becomes also an important consideration. So one of the things that we tried on this that has been quite effective is where we have the calculated output to only communicate that if certain criteria are met here. So the criteria is the output has to change by more than this deadband from the last communicated value. So periodically, we're going to evaluate this. We're not evaluating it constantly. We do it periodically. So if we have exceeded the deadband and we have gotten a response from the last right command, then it's valid to actually output a new position to the valve. This then minimizes the number of times you're actually going to be changing the output. There's this default time which says if I haven't changed by more than the deadband, but the time since my last communication has exceeded the default, then go ahead and communicate it anyway. And that allows you to drive the output to exactly a value, not being limited by this deadband in terms of your resolution of what you can get to. Okay. So that's what has been used in terms of minimization of movement. The other thing that we are working with is a new HART command. So using WirelessHART for wireless communication is introducing a new command. So the new command is something called time to apply, which says that when I ask for a change in position, I also communicate with it when the valve should change in the future. Because if you look at this, we'd really like to know where the valve is to be able to use that in our positive feedback network. But if we have a delay going down and a delay coming back, you really can't sense at any time the position. But if when you send out a change command and you say in the future it's going to change, it then becomes very possible to always calculate where the valve is, even though you can't measure where it's at. Okay, so this new command called time to apply is something, and this sort of illustrates the fact that in some cases when you send out a request, it may take 3 seconds before the valve gets it. Another time it may be 1 second. But if you set a time to apply, say, of 4 seconds, then you always are going to know when the valve actually changed, even though you can't sense it, even though you can't measure it at that point in time. So you can calculate it. So then the combined scheme then is this minimization of movement by looking at dead time period and default to use this time to apply command, and then we can then calculate where the valve is, even though we can't sense it. And so this allows us to do a very effective job here. In terms of event trigger, our output change is event triggered. The actual update of our control is really triggered by new communication. But you notice it's also a blend of continuous operation. That is, this PIDPlus is maybe executing every 200 milliseconds, even though the measurement is updated every 8 seconds here. The reason for that is that as soon as a new measurement comes in, you don't want to wait in terms of taking action. You would introduce more delay in terms of your control. So it's an important consideration. So this sort of shows in a simulation environment where we're comparing a wired PID with a wired valve and wired transmitter to a control loop where we have a wireless valve and a wired transmitter. So for set point change, where we have 3-second delay going down, 3-second delay going up, you notice that it's very stable in terms of control. You do notice that delay, though, in terms of the response, just due to the fact that this time to apply puts some delay in terms of the response you see. But from a control and stability standpoint, we're very good in terms of that. In this case, we took exactly the same control loop, exactly the same tuning, no change in tuning, but we changed the delay down and back to 6 seconds. Rather significant delay. And you notice, again, very stable operation, no futzing with tuning, no changes there. This shows a combination of wireless transmitter and a wireless valve in a simulation environment, where on their wireless transmitter, the period was set at 6 seconds. That means the device wakes up every 6 seconds. And if the change in measurement exceeds 3%, then it actually would get communicated. Otherwise, it wouldn't get communicated unless the time since the last communication exceeded 12 seconds, and then it would be communicated anyway. Okay, so this again shows the combination of wireless valve, wireless transmitter, no change in tuning. It behaves very, very well, very stable. So you can do a lot of things in a simulation environment that when you actually get out into the real world, things don't quite go the same way. And so we've done quite a bit of testing, both at customer sites and in-house. And fortunately, one of the divisions of Emerson is Fisher Controls. And so they have one of the world's largest flow labs up in Iowa. And so we have the opportunity to go up there and work with them, where you're using flow rates and valves that are of industrial size when you're actually doing testing. So in this particular case, this was our setup in one small corner of their flow lab. We had a valve that we could adjust, introduce disturbances into the line. And we then had our prototype wireless valve over here, sort of not shown so well on the right-hand side. So we could then control flow rate with our valve. We could introduce disturbances by changing this restriction downstream. So it allowed us to both test for set point change as well as unmeasured disturbances in terms of control. So we really did quite extensive testing of this. Wireless measurement, wireless valve, any combination of wired and wireless. Using the minimization, not using minimization. So we did some really very extensive testing of this. The time to apply in that particular case, this is sort of a histogram of what we actually saw there. So you notice the actual time to apply was somewhere around 6 seconds to catch maybe the half of what's going on. In our testing, we actually used 8 seconds as the time to apply. So that's sort of reality in terms of this unscheduled downstream communication and unscheduled response going back. So you notice it's really quite substantial in terms of the delay. This is the setup where we're using a wired transmitter and a wired valve in this flow loop in the flow lab. And you notice there's some interesting dynamics that are going on in here, introduced by these tanks in terms of some of the changes that are going on. But we used the tuning that was established by the on-demand tuning capability of the control system. So we didn't want to be accused of actually futzing with the tuning and doing something special. This is what came out of the tuning package that normally is used by customers. So you notice the response is pretty good. About a 3-second time to respond, response time, dead time plus time constant, about 3 seconds. Here's where we're introducing that downstream valve, changes in it. The control then had to respond to those unmeasured disturbances. And so you notice it had to do quite a bit of work to compensate for that. Okay, so here's where we had a wire transmitter combined with a wireless valve with our time to apply of 8 seconds. So the tuning that we used here is exactly the same tuning that we used here for wired. No futzing with tuning at all. So tuning is only based on process dynamics. So you notice a very good response, stable, no hunting or other things going on. Here's the response for an unmeasured disturbance downstream. Again, had to do quite a bit of work to correct for that. Here we used a wireless transmitter, wired valve, looking at that, and then the response for disturbances. And here we then showed wireless transmitter and wired valve. So the combination of two, the totally wireless loop. And again, you notice there is a delay due to the time to apply, but the actual response is really quite good, we thought, given all the considerations that we had to address here. So very stable operation, no hunting, no changing and tuning to do that, going from wired to wireless. And that's the disturbance rejection. So we're doing some more testing of this. We're working with a major oil company right now in terms of looking at putting this out in the Bakken area, doing some totally wireless control in the oil fields. But something that's a little bit closer to home is UT. We're located in Austin, Texas, and UT is just down the road from us. And they have a wonderful facility called the J.J. Pickle Research Center. So it's many hundred acres of facility. And in one corner of that, there's the separation research unit, where they have two fairly large distillation columns. And so oftentimes when we're trying new control techniques like wireless, we'll be trying it out there. Very close to industrial size unit. This is a new process that they've put in called a divided wall column, and Willie will be talking about that on model predictive control. This technology is something that in Europe, I think you're a little bit ahead of us in terms of using this divided wall technology. Basically, a divided wall column technology, you can do ternary separation, that is, separate three components using one column. Normally that would take two columns to do. And so you can get about a 30 to 40% energy reduction by going to this technology. But one of the problems of that is that you have a lot of interactions when you start doing that kind of thing. So it becomes a control challenge. And we've been working with them on terms of the control definition, commissioning. But on that unit, one of the things that we're going to be doing here in the next few months is actually putting in these wireless throttling valves. You know, they're working with hydrocarbons there, so we have to have Class 1 Div 2 certified devices to go into that. So we're sort of waiting to get those kinds of devices that we can then put in. So it's put a little bit of delay in it, but you notice here liquid flow, steam flow are going to be done wirelessly, and steam flow, liquid flow. So we'll be doing quite a bit more demonstration of this technology on a fairly important process on some fairly critical loops there of the unit. So in summary, this wireless throttling valve is something that you'll be seeing here in the near future. PIDPlus works quite well with this time to apply. So blending the two technologies, that is wireless measurement, wireless valve, is something that very much is doable without much problem there. We have done fairly extensive testing using a prototype wireless valve. A more commercial version of that we'll be actually deploying in some instances here later this year. So the future is that with wireless throttling valves, that's going to become a reality in certain applications. That's going to be an important part of addressing those applications. There's this book that we did here last October. It really summarizes about 10 years of work in terms of wireless control. So not to plug it to get any royalties. All the royalties from the book go to a university. We just donate them. Okay, but if you're interested in knowing a little bit more about PIDPlus, wireless valve, the testing that was done in the flow lab, that goes into infinite detail on a lot of these things. So, want to acknowledge Rosemont Fisher Controls. We've worked very closely with them in terms of this wireless technology, going all the way back to 2004. When the WirelessHART specification was first being developed. We started working with these different divisions of Emerson, looking at control and how it would be applied with wireless. So a lot of work between different organizations. Eastman Chemical is working with us on this divided wall technology at UT, so they're also a real contributor, and it's a company that we wanted to acknowledge here. So with that, I'll be glad to answer any questions. Yes.
Thank you, Terry, for a very nice presentation.
Oh, thanks.
The histogram you showed was the delay between the controller and the actuator. I assume
that's right.
You could have a similar histogram for the delay from the sensor to the controller?
No, for the sensor to the controller is really quite good because the difference is that on the measurement side, That's all schedule communication. It just a schedule automatically gets created for your wireless network. And so you have a 10 millisecond slot to communicate. So when we say, like with window communication, we have periodic, that is the period. That's the time when the device wakes up. If it wakes up and says, well, I think I need to communicate because I've had a change, it doesn't have to worry about contingency with something else needing bandwidth. That is its bandwidth at that time. And so you get very, very little delay in terms of the actual measurement getting up to your gateway.
So you use contention slots in WirelessHART for the communication between controller and actuator?
Yeah, and that's...
Schedule slots
in
superframe in the other consensus.
Right, so there are open spaces in the schedule, so it has to sort of wait for that open space. And that's why you're seeing such delays going down. Now, there is in the WirelessHART specification and in the standard the ability to do what's called downstream publishing. And but at least on our gateway, it doesn't support that right now. We're working on that, and that will dramatically reduce this delay going down.
Question on what is the lifetime of current batteries with valve?
Oh, with
I think that's interesting.
Are you increasing the lifetime?
yeah. That's sort of a contentious question in a way. Yeah, no, there are different thoughts on that right now in terms of how that will be done. But one approach is you provide a local power for the valve. And that's not a problem if you have a motorized actuator. It's just not a problem. And in a lot of these upstream applications in oil and gas, you're dealing with motorized actuators. So you have all the power in the world there. If you're looking at other applications, then there's technology, let's say, out there where if you're not moving the valve, it requires zero power other than the communication. Okay, and with that technology, it's possible, I think, to have battery-powered throttling valves, sort of like we have these on-off valves are battery-powered. You get 5-year battery life with them. So you can do some things in that area. But in terms of the initial delivery of this throttling valve, it'll be probably local power to it, and probably not too far after that, hopefully battery-powered as well.
I mean, an interesting observation, you talked about it sort of in passing, that if you have event-based communication, you have faster cycle times in the controller. You have sort of turned things around.
Oh, we have.
With wired communication, you want to communicate often, even if you don't execute more than every second, because you want to minimize the delay.
Right.
And here you do it the other way around.
Yeah.
You communicate less often or event-based, but then you need to execute often to minimize the delay.
Yeah. No, I'm glad that you picked up on that. Yeah, that's really true. It's like taking the cart and the horse and just turning it 180 degrees, right? And and that's an important aspect of being able to do this successfully. So.
Is the rate action often used also with PIDPlus and so on, or you?
We're using it on some temperature loops where it's wireless.
Interval changes because of the tuning.
Haven't seen any problems with that in terms of the rate calculation, the way we've done it there. But on all the temperatures on that distillation column are all wireless. You can't get it any other way. And so we've done a lot of temperature control, and some of that, and they are using rate. Yeah.
Okay.
Okay. Good.
Thanks a lot again.
Yes. Thanks.